Hi, everybody. So in this lecture, I'd like to talk to you about electric currents. So we define electric current as the rate of the flow of charge through a conductor, usually. And the equation which defines that rate of flow of charge is the amount of charge delta Q that flows past a reference point during a time delta T. So the amount of charge delta Q divided by delta T is the current. And since we're dividing charge by time, that gives us a coulomb, which is the SI unit of charge. Second is the SI unit of time. And so our SI unit will be a coulomb per second, which is an amp. So 1 amp is 1 coulomb per second. So here's a little picture of that. If you imagine a wire, which is usually a long cylinder, right? And you look at a cross section of your reference point. And if you look at the cross-sectional area of a long cylinder, the cross-sectional area would be a circle, right? So here we show a sort of side view of a circle, and that wire then would have a cross-sectional area that we call A. So what we're looking at is the flow of charge through that reference point, through that little circle, during a given amount of time. So it shows a flow of charge here moving past that reference point. So we're assuming here that the charges are moving perpendicular to that surface, that reference point surface, the cross-sectional area. And then you look at the amount of charge delta Q in a time delta T that flows past that reference point. And that will be the average current that flows past that point in a given unit of time. Now, let's take a look, though, at what's actually happening on a nanoscale level for this. So if you think of typical current flows, you're generally thinking about the flow of current through a metal wire. So let's talk about metals first. Now, in a metal, the charge that flows around are those free electrons. The electrons are the charge carriers. So remember that our model of a metal is that you have these ionic cores of the metal, and then the outermost or most weakly bound electrons to each atom are the free electrons or the conduction electrons. And each atom gives anywhere between 1 and 3 electrons and frees them so that they can move around. So we treat conductors in what's called the Drude model of conduction as a regular array of ions in 3D, and then electrons kind of roaming freely between those ions. So this means that the conductor is net neutral in charge because, for example, if each atom gives 1 electron to the C or free electrons, then the ion that's left behind would have a charge of plus E. So plus E for the ion and minus E for the electron means neutrally charged over the whole metal. So in the absence of an electric field, the electrons are still free, which means that what's happening is the conduction electrons are just kind of roaming around the metal, and they're doing it in a random way. They might move left, right as often, up, down as often, in, out as often. So on average, there's no net velocity of the electrons, which means no net current. And when they do that, their speed in between collisions is really fast, on the order of 10 to the 6 meters per second or so. So that's what's going on inside a conductor where there's no net electric field or voltage applied to the conductor. But now let's say that we hook our metal up to some source of voltage, okay? That voltage establishes an electric field. Now here in this little cartoon, we have our electric field pointing to the left, which means that negative charge carriers would want to move right? Electrons would want to move upstream on an electric field line. So now what's happening is that your electrons are moving around, and they will net move to the right. However, what's going to happen is they'll feel a very large acceleration. Remember, you set Newton's second law, ma equal to QE. And because you have a large acceleration there due to the small charge on the electron, you've got a large acceleration. And so the electron speeds up really fast, but there's always something to run into. And so your electrons take this kind of zigzaggy path that you see here. They'll go really fast and they'll run into something, and really fast and run into something else. So that means that instead of having a very, very fast net velocity, they would have a much slower net velocity so that their average speed is pretty slow. And this average speed is often called a drift speed, just to get you into a little bit of lingo there. So in a copper wire, for example, copper contributes 1 free electron per atom to the current, And if you look at a 12 gauge copper wire carrying a 10 amp current, then your drift speed would be a whopping 0.22 millimeters a second. So, you know, a quarter of a millimeter per second is how fast these electrons are drifting along. And this millimeters per second, or a fraction of a millimeters per second, is a typical order of magnitude for drift velocities. Now, it's important to understand a lot of students have the conception that you have a battery and then ultimately all the charge comes from the battery that's flowing in the current. No, no. What happens is the battery establishes a voltage or an electric field in the wire. The electrons are already in the wire because, you know, you have these ionic cores and these free electrons. So when you set up a voltage in the wire, that establishes the electric field, and then the electrons that are already in the wire move in response to the field. So the battery doesn't supply the electrons, it establishes the field instead. Okay, so I often ask this clicker question in class and have students think about it and come on, let's read it together because I do want to talk about this. You turn the ignition key in an automobile and you complete a circuit from the negative battery terminal through the electric starter and back to the positive terminal. This is a DC circuit, and the electrons migrate through the circuit in a direction from the negative battery terminal to the positive terminal. So how long must the key be in the on position for the electrons starting from the negative terminal to reach the positive terminal? Okay, so if you're talking about an electron that starts at one part of the battery and moves to the other part of the battery, right? All the way around, completing the circuit. Remember that we said that the electrons travel on the order of millimeters per second, right? So that's not very fast. And so I would think that since it's only going a millimeter a second or so, it's going to take a while, maybe an hour or so, for that electron that starts at the negative terminal to make it all the way back to the positive terminal of the battery, because it's got to travel through, I don't know, many inches, or at least say maybe a meter of wire to get from one to the other and back again, right? It's a good distance of wire. But now here's question 2. How long does it take to get the car to start the ignition? Well, that's just a fraction of a second, isn't it? Because what happens is the current is established immediately because of the voltage that comes from the batteries. So all the electrons in the circuit, all along the way, all in all the wires, all start to move at once. So it's not like you have to wait for that one electron to make it all the way around for the car to start. You flip, for example, the switch on a light switch on the wall, and the lights turn on very, very, very quickly, right? A fraction of a second, because the field establishment doesn't take very long. So that's the difference there. Okay, now we've been talking about charge and motion of charge and currents in metal wires, but I think it's important to understand that not all charge carriers are electrons. So for example, to borrow something from biology, what carries currents in our body? It's usually ions. Primarily sodium ions and potassium ions that are carrying the currents for the electrical signals in our body. So it's not electrons, we're not a metal, okay? So depending on what you're studying, different things can be the charge carrier. It might be an ion, it might be an electron, it might be in a semiconductor, electrons, or it might be the holes that are left behind from the electrons in a semiconductor that are the charge carrier for the circuit in question. So although I'm talking mainly about metal and conduction in metals, because that's really important for household wiring and everyday use and things like that, it really depends. Anything that has a net charge can carry a current. Okay, so let's get back to typical circuits again for just a second. Let's talk about what it takes to establish a current in a wire. It's not enough just to have a battery and hook a wire up to it, right? In order to have current flow, you have to have a complete circuit. And a complete circuit is one where the current can flow all the way around, going from, for example, the positive terminal of the battery to the ground, or in a wall socket from the positive to ground, okay? So if you look here, this is a little battery that this person has hooked up to a light bulb, and they have it leaving from the positive terminal of the battery to the light bulb, to the other side of the light bulb filament, and then back to ground. So that's a nice complete circuit. And so the light turned on. But notice that that doesn't really look much like what's going on in the schematic. So here you have the positive and the negative. This is our schematic symbol for a battery here, you have two parallel lines, one longer than the other. The longer one represents the positive battery terminal. Usually wires are just lines, okay? And then the current would flow as defined here from the positive terminal to the ground, because remember, we define current in terms of the direction that positive charges would go. And then you have this device or load here in the circuit and then back to ground. And so you can see here that our little schematic, it doesn't actually look much like the physical circuit, but that's okay. Okay, so by convention, thank you, Ben Franklin, current is defined as flowing from positive to negative. And like I said, maybe in the body, right, where you have sodium and potassium positively charged ions carrying a current, that would be what is happening. But in a metal wire, it's actually the electrons that are the charge carriers, okay? And so remember that electron flow is opposite to the direction of conventional current. So we define conventional current as going from the positive to the ground, right, on your battery, and then that would be clockwise here in this circuit, but the electrons actually go opposite to that. So that's just a convention. I mean, hey, Ben Franklin had a 50-50 chance, and the coin flip he got wrong, but then later on we had semiconductors, so maybe he wasn't so wrong in the first place. So there you go. Okay, when the current in a circuit has a constant direction, like from a battery, the current is called direct current. So most of the circuits that we analyze in this algebra-based physics class will be assumed to be in a steady state with constant magnitude and constant direction in a direct current scenario. So most of the stuff that you do is going to be direct current. Now, because we're not talking about any kind of loss of our battery, the voltage between the terminal of the battery is constant. The battery produces direct current. And you also might hear a more old-fashioned term for voltage, and you think of the battery as being a source of EMF, and the old-fashioned terminology is that, and that stands for electromotive force. Now, when the term EMF is used, it's a voltage, okay? So basically that's what it means. It's a voltage source, a battery. That's what EMF means. Now, it's not a force, even though force is in the name. So please don't get those two things confused. I apologize for that. If it were up to me, I'd wipe it out and just call everything voltage. But it is a holdover from more old-fashioned stuff. Let me do an example problem for you. Suppose you have 5 amps of current flowing through a metal wire. How many electrons will flow past that given point in the wire each minute? Okay, so this is the kind of question that often gets asked on physics homeworks. So let's go through how to do it. So remember that we've defined current as delta Q over delta T. Okay, so delta Q is the amount of charge in coulombs that flows past the point. But remember that that actually also counts to a number of charge carriers, right? How many charge carriers is that? That's what the question is asking. So in order to figure out how much charge, right, you would need to multiply the number of charge carriers times the charge per charge carrier, right? So N, we'll call capital N, the number of electrons that you have, and then we call lowercase e, the amount of charge that each electron carries, okay? So then delta Q is the number of electrons times the charge of an electron. So delta Q is Ne. And then if you cross multiply there, you can see that that delta Q, according to our equation, would be I times delta T. So delta Q equals Ne equals I delta T, okay? Now, the charge on each electron, you can figure this out from Googling it or looking it up in the front cover of your textbook. The charge from each electron is 1.6 times 10 to the minus 19 coulombs. That's the amount of charge that an electron or a proton has in the magnitude. So it's N times 1.6 times 10 to the minus 19 coulombs is equal to the current times the amount of time. Now the current, it's given in the question, is 5 amps. And the amount of time is each minute. But remember, a minute is not the SI unit of time, the second is. So how many seconds is a minute? 60. So N times 1.6 times 10 to the minus 19 coulombs is equal to 5 amps times 60 seconds. And then to solve for N, we just divide each side by the charge of an electron. And when we do that, plug everything into our calculator, we get N is equal to 1.9 times 10 to the 21. And that is the number of electrons that flow past the given point in the wire each minute. All right, well, I hope that that was a gentle introduction to current for you and you enjoyed it. And I'll see you next time.